space, the final frontier.
Supersymmetry was first considered for removing infinities in matter fields and Yang-Mills fields in a space-time where both the ordinary number dimensions and the Grassmann dimensions were flat, not curved. But it was natural to extend it to ordinary numbers and Grassmann dimensions that were curved. This led to a number of theories called supergravity, with different amounts of supersymmetry. One consequence of supersymmetry is that every field or particle should have a superpartner with a spin that is either 1/2 greater than its own or 1/2 less. Spin of particle. All particles have a property called spin, having to do with what the particle looks like from different directions. One can illustrate this with a pack of playing cards. Consider first the ace of spades. This looks the same only if you turn it through a complete revolution, or 360 degrees. It is therefore said to have spin 1. On the other hand, the Queen of Hearts has 2 heads. It is therefore the same under only half a revolution, 180 degrees. It is said to have spin 2. Similarly, one could imagine objects with spin 3 or higher that would look the same under smaller fractions of a revolution. The higher the spin, the smaller the fraction of a complete revolution necessary to have the particle look the same. But the remarkable fact is that there are particles that look the same only if you turn them through 2 complete revolutions. Such particles are said to have spin 1/2. The ground state energies of bosons, fields whose spin is a whole number, 0, 1, 2, etc., are positive. On the other hand, the ground state energies of fermions, fields whose spin is a half number, 1/2, 3/2, etc., are negative. Because there are equal numbers of bosons and fermions, the biggest infinities cancel in supergravity theories. Superpartners. All known particles in the universe belong to one of 2 groups, fermions or bosons. Fermions are particles with half-integer spin, such as spin 1/2, and they make up ordinary matter. Their ground state energies are negative. Bosons are particles with integer spin, such as 0, 1, 2, and these give rise to forces between the fermions, such as the gravitational force and light. Their ground state energies are positive. Supergravity theory supposes that every fermion and every boson has a superpartner with a spin that is either 1/2 greater than its own or 1/2 less. For example, a photon, which is a boson, has a spin of 1. Its ground state energy is positive. The photon's superpartner, the photino, has a spin of 1/2, making it a fermion. Hence, its ground state energy is negative. In this supergravity scheme, we end up with equal numbers of bosons and fermions, with the ground state energies of the bosons weighing in on the positive side and the fermions weighing in on the negative side. The ground state energies cancel one another out, eliminating the biggest infinities. There remained the possibility that there might be smaller but still infinite quantities left over. No one had the patience needed to calculate whether these theories were actually completely finite. It was reckoned it would take a good student 200 years, and how would you know he hadn't made a mistake on the second page? Still, up to 1985, most people believed that most supersymmetric supergravity theories would be free of infinities. Then suddenly, the fashion changed. People declared there was no reason not to expect infinities in supergravity theories, and this was taken to mean they were fatally flawed as theories. Instead, it was claimed that a theory named supersymmetric string theory was the only way to combine gravity with quantum theory. Strings, like their namesakes in everyday experience, are one-dimensional extended objects. They have only length. Strings in string theory move through a background space-time. Ripples on the string are interpreted as particles.